In this talk, I'm going to focus on the other research line on how we can structure extreme ultraviolet beams by controlling the process of high harmonic generation. Among the different properties of light, we can distinguish two types of angular momentum. On the one hand, the spin angular momentum encodes information about the polarization state. On the other hand, certain light beams carry orbital angular momentum. They are known as optical vortices, and they are characterized by an helical wavefront, or equivalently by an azimuthal dependence of the phase. The parameter characterizing the geometry of an optical vortex is the topological charge, L, which indicates the number of wavefront twists in one wavelength. An optical vortex is characterized by the phase singularity at the center, which implies that the intensity in this point has to be null. So the intensity profile of an optical vortex has a donut shape. In general, optical vortices are scalar. They have just one unique polarization state. But we can also build up vectorial vortices where at different positions we can have different polarization states. So in the case of a vectorial vortex, at the center we have both a phase and polarization singularity. Our goal in this work was to upconvert the scalar and vectorial vortices to the high frequency regime. And we used high harmonic generation since this is a route towards higher spatial and temporal resolution in the scale of nanometers and attoseconds. In all, the tool of high harmonic generation has been very important for extending the field of structured light beyond the optical range. The key idea is that we can transfer the properties of an infrared driver to the extreme ultraviolet or soft X-rays, because all the information is encoded in conservation laws. The only restriction that we need to take into account is that in the three-modal step of high harmonic generation, the recombination step only occurs for drivers with a low ellipticity. So we need to keep this in mind for something I will comment on later. And for these calculations, among the different possibilities that Javier has commented before, we are using the strong field approximation and then the electromagnetic field propagator to have the signal at the far field detectors. So one of the first works to upconvert a structured beam in the extreme ultraviolet was done in my group in Salamanca. So they demonstrated that when we drive high harmonic generation with an optical vortex, with a pure scalar vortex, the topological charge scales linearly with the harmonic order. So in case that we have a driving beam with charge L equal 2, the 25th harmonic beam will have a topological charge L equal 50. And in these bar plots, I'm showing the results of doing the azimuthal Fourier transform of the complex field. So we can clearly see that we are in a single pure mode situation because it's a theoretical beam. Then the superposition of several harmonic orders with different topological charges give rise to attosecond light springs in the spatiotemporal domain. What we have done recently is to analyze the case of the upconversion of an experimental scalar vortex. So our collaborators at Paris-Saclay were able to characterize both the driving beam and the 25th harmonic by using Harman sensors. So these Harman sensors allows to characterize both the intensity and wavefront, so we have a full spatial characterization of the beam. And in this case, is different from the one I have shown before. This is a charge L equal 4. So the 25th harmonic should have a charge L equal 100, which is close to what they obtain in the experiment. And by driving the process with higher topological charges, we can reach very high topological charges in the extreme ultraviolet regime. And well, from the characterization point of view, from the experimental point of view, this is quite challenging because we require a very high resolution to detect this rapid variation of the phase. And this can be important for that line to transfer orbital angular momentum from light to matter as we reach higher topological charges. Then from the modulations in the intensity profile, we can infer that there is some modal contamination. Indeed, if we do the azimuthal Fourier transform in this case, we observe that minor impurities in the driving beam are greatly amplified in the process of high harmonic generation. And we have checked this also in our numerical calculations, where we take as input the experimental driving beam, and then we are able to qualitatively reproduce with the experimental results. So we have the modulations in intensity, the variation of the wavefront, and a modal spectrum with the same peak value, even if we are just simulating a transversal plane, but not the longitudinal propagation along the medium. But just let me comment more about these bar plots from the azimuthal Fourier transform, because this gives us an idea about the purity of the beam, but it may not be the perfect measurement of the variation of the phase. Because when we do the azimuthal Fourier transform, we are calculating the variation of the phase, assuming a perfect cylindrical symmetry that is not present in an experimental beam. So it should be probably better to follow the variation of the phase along the ring of peak intensity, which this would give us a better idea of the orbital angular momentum, and which probably is more important for the experiment. Finally, we will talk about the upconversion of a vectorial vortex. So in this case, the driving beam is structured both in phase and in polarization. And we obtain similar results to the case of a scalar vortex. We also obtain attosecond light springs, but now with a spatially varying polarization. So we can, for example, have an attosecond light springs with radial or azimuthal polarization. Then a similar selection rule applies in high harmonic generation if we consider the Pancharan-Mann topological charge. This charge is defined in terms of the Pancharan-Mann-Berry phase, which considers the intertwined phase and polarization properties of these beams. If we, in this case, a vectorial vortex is a superposition of two circularly polarized scalar vortices. So when we analyze when we perform the azimuthal Fourier transform of the left circular component, we obtain this topological charge. If we do the azimuthal Fourier transform of the right circular component, we obtain a different topological charge. It is a superposition of these two eigenmodes. And the Pancharan-Mann charge is, for this case, is for the driving beam and the harmonic beam, the average between the two circularly scalar vortex, circularly polarized scalar vortices. So when we upconvert a vectorial vortex into the high frequency regime, we need to take into account of the driving beam evolution during propagation. As I said, this is not an eigenmode of the propagation operator, so the properties change during the propagation. We can generate a very clean extractor of a vectorial vortex, of an infrared vectorial vortex at a certain plane, but as this beam propagates towards the gas target, it evolves to a complex distribution where we also have high ellipticities. This is because the two circularly polarized modes do not perfectly overlap at the gas target. So it is what we obtain in this experimental characterization of the circular polarization. But the question is, despite this fact that a vectorial vortex is not an eigenmode of the propagation operator, so that we have all this complexity, can we generate an extreme ultraviolet vectorial vortex from an infrared one? And the answer is yes, we can do it, because high harmonic generation is only efficient in this region of low ellipticities. And so the harmonics are generated with mainly with a linear polarization and a much simpler profile at the gas target. And what is more important is that the main features of this harmonic beam are retained in the propagation towards the far field. So the propagation of the high harmonic beam is much more robust than the propagation of the infrared vector vortex, as we see in these results where the main properties are concerned. The only evolution that we observe is the rotation of a smooth rotation of the polarization structure from the near field to the far field. If we observe at the vertical polarization projection at the gas target, this will correspond to a radial polarization. But if we observe the same component at the far field, this would correspond to an early azimuthal polarization. And we can understand this in analogy with the circular birefringence that is present in some chiral media, for example, where the different circularly polarized components introduces a dephasing between them because they see a different refractive index. In this case, it's the same, but it is in vacuum. But the phase difference between the two circularly polarized modes arises due to the GUI phase, because they have a different topological charge, so their GUI phase is different. And this is important because it's not just that we are combining the properties of a vector beam and a vortex beam, because these beams also carry orbital angular momentum. So we have the spatially dependent polarization and the orbital angular momentum just in one beam. But also these beams have some additional properties, like this 3D polarization structure. That is, we are not just structuring the polarization in the transversal plane, but this polarization is also rotating in the longitudinal direction. And as a curiosity, then you notice, well, here in the far field, it seems to be like the tilt does not correspond exactly to an azimuthal polarization. And what we have observed in our simulation is that this is an effect of the intrinsic dipole phase in high harmonic generation. So if we switch off the intrinsic dipole phase, we will have a perfectly azimuthal distribution, but the dipole phase introduces an additional tilt, which could be used as an indirect measurement to obtain the phase of the electronic wave function in high harmonic generation. And finally, there is another different behavior in the case of a vectorial vortex compared to the case of a scalar vortex, is that the HAG efficiency increases for drivers with higher topological charge. And this can be understood because if we see in this bottom row plots how is the intensity and the ellipticity of the driver, we see that for higher topological charges, the ring of zero ellipticity approaches the ring of peak intensity. And also the slope of the ellipticity flattens. So basically, there is a better superposition of the right and left circularly polarized modes for higher topological charges, which leads to a bigger region where the ellipticity is low, and this region has a higher peak intensity, which leads to a higher HAG efficiency. In conclusion, we demonstrate the robust generation of XUV scalar and vectorial vortices. Our numerical calculations have helped to the experimental group to characterize very high topological charges. And this paves the way towards reaching higher topological charges or higher purities in the EUV structure beams. But probably more interesting is to think in new scenarios of light matter interactions that can be explored with these ultra-fast beams structured both in polarization and phase. And for example, we can think in how they interact with chiral molecules, with topological materials, with magnetic materials, etc. And finally, well, I just put all the authors that participated in these references, which this has been done in collaboration with the University Paris-Saclay, with the group of Sofika Zamias, then with some fruitful discussions for Charles Darby in the Colorado School of Mines, and with the support of Imagine Optic for the wavefront characterization. Finally, I thank you for your attention, and I'm open to any questions or comments you may have.